next speaker. Let me have a slide for this. So Adam, are you here?
I'm here, Yang.
Hi.
Good morning.
Good morning. How are you? Hi. Our next speaker is Dr. Adam Hopkins. He is Dr. Hopkins is actually my colleague of mine when I was at Princeton. We're from the same group. He's a entrepreneurial and a scientist focused on commercialization and breakthrough technologies in the physical sciences and novel materials. He's the founder of and for the past 7 years has served as the CEO for the Uniformity Lab, a rapidly growing additive manufacturing materials, software, and printing company born out of the IP conceived and developed by himself and Princeton professor Salvatore Torquato. He led the technical and business teams like the high-tech startups developing novel thermoelectric, photonic, and phonic materials, and he's the author of several material and manufacturing processes patents, including on the topics of granular material densification enhancement, additive manufacturing, printing processes, and thermoelectric design production, and phonic attenuation. He earned his PhD in theoretical chemistry from Princeton, where he was awarded the Honorific Fellowship and the Ray Grimm Prize in Computational Physics, which is a very significant achievement. And also, Adam obtained his bachelor degree also at Princeton in physics with minors in materials and applied mathematics. So today he will tell about his very, very interesting work on the frontiers of metal laser powder bed fusion and binder jetting. With that, go ahead. Let me stop share. Let me stop share and
let me share my screen. Yeah, thanks very much, Dr. Zhao. And may I add a lot of the fundamental research underpinning, or the fundamental discoveries underpinning some of the dense powder technology that we work with at Uniformity Labs, where a lot of the advances were made with an algorithm that we've called the Torquato-Zhao algorithm. So thanks very much, Yang, for a very substantial contribution in that respect as well. Cheers, and thanks for the introduction. So I'm going to talk about today metals additive manufacturing, and I'm going to approach this from a commercial aspect and also a technical aspect. So what are the problems that are seen in the industry today? And I'll give a little bit of background on my perspective, where I'm coming from when I say what are the problems. So these are problems in commercializing the technologies, and I'll focus on laser powder bed fusion and on binder jetting, and I'll give some primers on what those are. Spend a little time on the physics of each, because those are they get interesting. And just as an example, on this picture you see here, this is binder jetting. That's a part of particles glued together. And by the way, I'll start from a simple framework, and pardon me if I'm overly simplistic, but just in case those are not familiar with the technology, I'll go into detail. But this is a bunch of particles glued together on the left, and that's after they've been centered to roughly 99.5% relative density, so essentially full density, or a machine density, or a cast density of material. Great. Okay, let me go to full screen mode here. All right. So background's covered. I'll start with an overview of technologies. Then I'll go into a little bit of detail about laser powder bed fusion and its physics. I'll borrow from works of peers. A lot of the work at Lawrence Livermore National Labs is quite exciting in this front, and areas of potential for development. So where the challenges are in laser powder bed fusion. And I'll focus on the most salient technological challenges or technical challenges that I don't think the commercial world can meet, as in the place where there's really a great opportunity for national labs to step in, or where they've already stepped in, or for academic work to step in and solve problems that might otherwise not be solvable by the commercial world. Then I'll move into binder jetting, same type of story. And I'll talk about data collection, because there's not enough of it right now to actually do a solid job of addressing some of these problems. So some background on Uniformity Labs. It's an additive manufacturing feedstock company that also develops print solutions. So we have 8 large or medium format printing machines, industrial printing machines for metal additive manufacturing, 5 laser powder bed fusion, 3 in metal binder jetting. And we work with the forefront of printing technology, and we work to deploy these ultra dense powders, which are roughly speaking, they're a bunch of big particles with different sizes of smaller particles filling the gaps between them. A little more to it than that, but for now, I'll say that. And we roughly work on deploying these products and learning how to print them in these machines. And in this process, we work with sort of the most advanced experimental printers that are out there. So we gain a pretty good view on what the problems are, not just with today's technology, commercialized technology, but with the technology that might be commercialized in 5 to 10 years. So some more stories there. We have various raw materials. We've developed, I believe, as many or more raw materials for binder jetting, different alloy classes, than anybody else on the commercial front. We have those available. And then with respect to powder bed fusion, we have materials available as well that introduce these substantial changes into the physics. And I'll only bring this up not to tout our company, but to point out that by changing the feedstock and changing the parameters in laser powder bed fusion, you can enact rather substantial changes. In fact, you can, for example, print with 2 to 3 times the throughput without changing laser power. You have to change laser speed, scan a little bit faster if you want to print faster. But then the result is the physics can be modified to achieve more reliability, less residual stress in the process, faster printing, things that the industry needs. And I'll touch on these pictures. That's a sintered statue. I'll point to these fingers that are about 100 microns thick. You can get brown parts that do not break. Brown meaning when they're glued together by the binder, and they've been cured before they're centered. And then you can center them without substantial warping if you're careful. That's a roll cage for a solar-powered race car that's racing in Australia right now that we made. Neat device. Encourage you to go online and take a look at that race if you like. That's a gas atomizer. That's how most powders are produced for these powder-based print technologies. That's Uniformity's gas atomizer. It's in Hayward, California. It's a big piece of equipment, but its goal is just to turn metal into nice spherical or roughly spherical particles of varying sizes. Again, that's Uniformity powder. This is 50 grams of powder. It happens to be 316L stainless. In each jar, you can see Uniformity powder is denser. Also flows really nicely. In jetting, it flows quite a bit more nicely. In other words, it has far less cohesion than other powders. And cohesion is very important to the spread and the uniformity of the spread on the bed. I'll get more to that later. So quick primer, laser powder bed fusion. You have a powder stage. It's not necessarily on the left, sometimes it's from above, but you distribute powder across the bed and layer by layer. So you put down 50 micron powder layer. In other words, you drop the build tank as it's dried by 50 microns, and you put powder on top. The thickness of the powder on the layer is not really 50 microns in this case, it's a couple hundred microns, sometimes 500. And then you scan a laser across the top in the outline or profile of the part you want to print. So if you wanted to print a pipe or an annular ring, you'd, roughly speaking, scan in a circle, and you'd melt. You seek to fully melt in laser powder bed fusion, that circle, and then you drop the build stage, spread more powder on top, and do it all over again. At the end of the day, you've got a pipe sitting in a bucket of powder, fully ready to go, possibly with some residual stress. Great. What are the advantages of this technology? It's very highly accurate, but you do have to deal with residual stress warpage as the part cools. But you can meet machining tolerances in many cases, provided you're properly supported. That's a big deal for the industry because almost every complicated assembly of parts is in fact specified to CNC machining tolerances. So you really want to meet those or come close to them so that you don't have to take your part out of the build bed and throw it into a CNC because that's very expensive. It works very well for easily weldable alloys. So eutectic alloys for aluminum like ALSI10MG or L357, 356, that's an aluminum silicon alloy. It doesn't work very well. I'll give an example later right now for, although there's some good work on this, on, for example, aluminum 6061. 6061 is the most commonly machined alloy in the world by tonnage. I think together all tonnage of 6061, machine 6061 exceeds all tonnage of all other materials in CNC machining. So it's an important one, but it's non-eutectic. It's aluminum with a bit of copper. It has phase separation problems as it hardens, as it solidifies. I'll touch on that again later. So it works for some alloys, it doesn't for others. You could make it work for these complicated alloys with careful approach, engineering and physics. And the machines are expensive, so problems. They're slow, you want to print faster, they're comprised of lasers and complicated optical parameters, they're in inert environments, they cost a lot of money. They're not as expensive as electron beam melting, but they are still expensive, so this is currently only viable for parts that are assemblies that are very complicated in geometry that you might not manufacture any other way other than laser powder bed fusion. But what you get out the door is very high quality material properties if you scan properly. You're paying enough attention, you're diagnosing your build properly. If you have a robust parameter set, you get repeatable properties, but that's not a given in the industry right now. In fact, most of the time people struggle with that. And you have these support structures. So when you support, meaning you need to build literally physical supports to obtain high tolerance, or I'll say high geometric fidelity. Those support structures need to be broken off or machined off, and again, that costs a little bit of money. So fewer supports are better. Jumping in, I'm going to skip directed energy deposition. It's also out there. It's not nearly as prominent as laser powder bed fusion or binder jetting, but it's there. I won't say much about it except you jet powder from a spray gun through a nozzle, and then you use a laser or a e-beam, electron beam, to melt that powder. As it strikes, you create this melt pool. And then it's somewhat similar to laser powder bed fusion after that, except you just don't have a bucket of powder that your part is putting in. Jumping to binder jetting, I'll spend more time on this. Same idea as laser powder bed fusion. You lay down your layer, except you use what amounts to a complicated 2D print head to glue, to lay down glue. I'll call it glue binder, but it's basically just glue to glue particles together. And you can do this on a 2D from a 2D perspective, so like lithography. So a single pass over the build prints an entire page like your 2D print at home. It's much, much, much faster, a little bit cheaper because lasers are more expensive than 2D print heads. However, then you're left with, as I showed on the first slide, a brown part or a green part, whichever one to call it. You have to cure the binder, and then you have binder in between or space in between particles that are glued together. And when you center this part, you put it in the oven, it has to shrink. It shrinks quite a bit, usually about 20 to 25% linearly. I'll put in a plug for uniformity powder. It's only about 10% uniformity powder because it's more dense to begin with. When it shrinks, it invites warp, and it doesn't shrink uniformly necessarily, nor does when you shrink do you get to full density in the way that you would with powder bed fusion. So instead of 99.9% of theoretical density, you might be at 95 to 98%, or if you have a really nice powder, you can get to 99.5%. Still not quite as good, but that's good enough, by the way, to get properties from the 99.5. So you shrink, you have some warpage, the part bends when you shrink, there are residual stresses, you have these thermoelastic effects, and it's hard to predict that. So your accuracy is not as good as powder bed fusion. If you make a big part, it can break. Those are problems, but at the end of the day, it's much, much less expensive. So if you want to think about deploying additive manufacturing in metals in the hundreds of thousands of tons, and we are thinking about this in the industry and looking to this in the future, say in the automotive industry, and the automotive industry is thinking about this and investigating it and spending money on it, then you need to be able to get accurately built larger parts. For that, you need to address the shrinkage problem, this cracking problem. You need to address the mechanical properties of the material, and most importantly, it needs to be repeatable. Great, so jumping into powder bed fusion. And again, I'm going to do a quick primer based on, I've pulled from a few papers from Lawrence Livermore as well as from uniformity results. If you don't know much about laser powder bed fusion, you want to know more, I highly recommend the references here. Great work once again. All right, so what we're looking at here is a scan track. So a simulated scan track on powder. This is at 240 microseconds after the laser comes on. This bottom one is at 670 microseconds. So as the scan path is to the right, as you can see here. As the laser moves to the right, you actually end up drilling a hole in the substrate, the metal below the laser. The metal below the laser absorbs most of the laser energy. The powder absorbs a little bit of it. And then as you move, you create this melt pool. Particles are blasted. If you've seen a high-speed video of this, particles are blasted all over the build chamber. They fall in from the sides of the melt pool into the melt pool, and they fly out due to basically they're little rocket ships. They get very hot very quickly. They plasmarize or vaporize, and it ejects them very quickly. I'll show some data on this in a minute. And some of them stick and melt. And you also have Marangoni convection going on here. So what you're doing is, as you move the laser away, this is a lower density, extremely hot melt that's at vaporization or close to it, some parts of it, the melt pool. And as it cools, you have Marangoni convection. So the lower density metal here, cooling metal, pulls the metal from the hot spot backwards, if you will. So in the opposite direction of the scan track. And that's what fills in the gap. This process is reasonably complicated. That's a point I want to make in spades. And it might even be a bit of a minor miracle that it works at all. You need to have a very carefully designed process window to get repeatable results. Here you can see the time screen and different cross sections of the laser on the right side here. The laser melting into the substrate, and it doesn't show the powder falling in, but the powder ends up falling in. And as you cool, you get these scan tracks that are these cylinders that stick up out of the build. So here's some scan tracks, uniformity built, just to show what scan tracks look like. And I think this is Inconel 718 perhaps on the Super Ally, but it's pretty similar. Okay, so a little bit more on that. Here are some cross sections at different powers and fixed speed, just melting into a plate. As you can see, you get very different profiles of melt pools. You get this wider profile at the top in 316L, this is. You get this dip, usually wouldn't scan this deeply. So this is when you're moving very slowly or at very high power. And I'll get to some equations later that help define this. This is what the tracks look like from a different perspective. Again, these are faster scans at this, lower power scans at the bottom, higher power scans at the same speed at the top. And then to show that this the scan track shape and size is highly dependent on the metal alloy and the laser properties. You can imagine it being dependent on the laser scan speed, the spot profile and size of the laser, but it's also tremendously dependent on the metal itself, its thermal conductivity. It's also tremendously dependent on the powder in a way that you can have scan tracks that are 4 times as large if you have different powder properties with all other qualities being the same. Particularly if you use denser powder, if you're able to get the melt pool cooler. That's been shown. So here on the bottom left here, I'm just showing some absorptivity properties. This is in a disk. That's the black line at 100 millimeters per second at different powers. Pardon me. You can see absorptivity peaks once you're drilling a deep hole. Once you're drilling a deep hole, the laser is absorbed in the center of the pit and then scatters into the sides of the hole. And so you lose very little laser power to scattering. However, when you're not very deep, you're scattering about the build chambers. Positive. And then here's in 316L powder. I believe it's a 100 micron thick layer. You can see you have far more absorptivity initially with lower powers. This again is 100 millimeters per second scan. The reason for that is you have a curved surface. Your particles have curved surface. There's higher absorptivity as a function of porosity of the powder itself. So the particles versus the space between them. That's what I mean by porosity or relativity. And then there's a crossover point here. That's at very, very high energy intensities relative to the laser process. When you're actually running the laser, you're more in this regime here, the early regime. So if you take a look at this middle track, that's a more common laser powder bed fusion position. You actually have more absorption for 316L powder than you do for just a substrate because of the absorptivity of the powder. But with that said, you can see they track a little more closely when you're in this regime where you would normally print. Then over here on the right, I'm showing it's extremely dependent on the alloy. Not surprisingly perhaps, but if you look at aluminum here at the bottom, you're basically not absorbing at all. These are discs, by the way, not powders, but yeah, you'll have a similar shape for powders as to this 316L shape. And 316L very different than aluminum or tungsten. They do eventually converge when you drill a deep enough hole, but obviously the physics are tremendously dependent on the alloy. So defect formation. So what's going on here? I'll start in this top left diagram. you have this melt pool, you have vapor, metal vapor being created by the laser. The laser skin depth on these particles is on the order of a few tens of nanometers or even a handful of nanometers. So very, very quickly, the particle, you are vaporizing components of the metal particles, and they are blasting out of the way. So a good analogy is taking a water blast or a water cutter and spraying it on sand. You're just blasting particles out of the way. Then you begin drilling into the substrate, as shown on the previous page, and then particles fall into the melt zone, into the hot zone, and that's how you get most of your material, is particles adjacent to the melt pool falling in. So naturally, when you get all this vapor, you have a blast. It blasts the particles first out of the way, so they fly out, but then you have a compression wave, a shock wave, and the gas pushes the particles back into the melt pool. Again, reasonably complicated process. And jumping to this bottom diagram here, this is a measure of the different types of ejectment of bits of particles that are flying out from the system. The cold particles are shown in red here on the bottom. There are a lot of those. Those are the particles that fall in from the powder bed, hit the hot melt pool, and become little rocket ships and blast out of the way. The stars are from recoil pressure. So that means you have so much energy going into the melt pool that your melt pool is dancing, if you will. It's moving around in an uncontrolled fashion, and it actually just it ejects particles. And then that's different from the ejectorate. These hot particles here, those are just little molten masses that are sprayed from the melt pool itself for similar reasons. So you have a lot of ejectorate is the point, and you can form defects with all this material going in and out of the melt pool. And these are different types of defect formation. So you need to figure out how to make this process repeatable. And it's complicated enough that this is not a simple problem, is the main point I'm making. All right, so a couple of equations that maybe make this a little bit more manageable. ED, energy density. Power, that's the laser power, divided by the hatch spacing. So that's if you're doing scan tracks, look at this figure in the middle top. You space them a certain amount of micrometers apart, say between 100 and 300, usually around 150 or 200, depending on the material, in actual operating regimes. And then layer thickness. So layer thickness is the amount the stage moves at every, not the powder stage, but the build stage. That's different from the powder layer thickness, which is usually a few times the actual amount the stage moves. So, but at the end of the day, your scan tracks are built on a layer thickness perspective, not a powder layer perspective. And then S here is laser speed, so how fast you're scanning. That's energy density, it's in joules per cubic millimeter. Here's a scan pattern that you might see. You have fill, where you scan in the middle. Then you have a contour, just a single scan around the edge. That's to take care of the problems you have when you turn the laser off after scanning these hatches, because turning the laser off introduces defects of various different types. I won't go into the details there, but you need a contour to fix those defects and to smooth out the surface of the part. There you can see tracks from above. They're very repeatable over most of the build, but if you're going to put a part in an aircraft engine or in space, very repeatable over most of the build doesn't cut it. You have a 300 micron pore or a 200 micron pore, you're really, in which is the size of the melt pool, width of the melt pool, you're out of luck. That part is going to fail potentially, and it's not useful in the commercial space. So you really need to be precise over a broad area of the part here. Here's a cross section of a scan. You can see the bottoms of the scan tracks here, and then you change direction. So this would be a different scan direction. And on the bottom here, here's some Uniformity Labs TIE 6.4. This is a nice etch of a micrograph. You do get anisotropic properties. This is a cut parallel to the buildup direction, this part. And here's zoomed in here. But you can get to 99, 98% density on some materials. Aluminum, silicon, magnesium, probably not. I'll get to that in a second. But on some like titanium and on 316L, you can do this, and you can do it quickly. You can see the edges are a little bit different than the middle. Sorry, I don't have a more zoomed in image. Great. Okay, going to the second equation, energy intensity. I introduced this purely to talk about aluminum, though it does come into play for some other materials at very slow scan speeds or very high energy density. Energy density I'll call power divided by the scan speed times the diameter of the beam when it strikes the plate. Technically, if you want to talk about peak intensity, I should use the diameter squared, or I should use the area of the beam profile, maybe a Gaussian beam profile. I'm using diameter because it interacts with the absorption properties as it heats the surrounding material. So if you think about drilling that hole I was talking about earlier, as it heats the materials adjacent to it, you actually get a dependence. It's linear, it's not on the square. So we introduce energy intensity in joules per millimeter squared. In this case, again, the DS is the spot size. This matters because your energy intensity is too high. You'll overheat aluminum. I think I've got a chart here. Yeah, there we go. And as you overheat that aluminum that's adjacent, so immediately adjacent to where your laser beam is, and by adjacent here, let me skip back so I can tell you what I mean here. If this is your drill, your scan track here, then I mean adjacent, I mean, to the left and right of this image. So in the lateral directions, not in the buildup direction. And what happens is you have supersaturated hydrogen in aluminum and some other materials in that solid. And if you have too much intensity, you heat that solid, and by the time the supersaturated hydrogen, it comes out of solution and drifts into the melt pool. And when it reaches the melt pool, the time scales are on the order of tens of microseconds for the solid diffusion of hydrogen at high temperatures, not for the liquid, such that the liquid, the top of the track has cooled, and you end up trapping the hydrogen. For the liquid supersaturated hydrogen, that just leaves in nanoseconds or even picoseconds. You don't care about that. It's a supersaturated hydrogen in the solid that matters. And here's what happens. So if you have this spot D4 sigma 56 microns, it's this regime where we're getting that supersaturated hydrogen migration into the melt pool, and it's being trapped. And then if we change the spot, all of the parameters identical to 92 microns, so just a little bit of a change in spot diameter, you can see you get rid of most of the hydrogen porosity because you're not, the length scales and the time scales are not proper for the retaining of that hydrogen in this particular case. All right, great. Energy intensity, I've given just an example of why it's important. Energy density is for most alloys the most important parameter. And I'll focus on one thing, that if you have denser powders on the bed, for example, I mentioned this earlier, then the energy densities you can print at, for example, for 316L, you can go into the 26, 28 joules per cubic millimeter range, which there's a whole mountain of commercial papers out there saying that's impossible. You have lack of fusion everywhere. You have defects everywhere. What do I mean by that? Hold on, I think I have some pictures. Oh, I may not, so I won't scan around, but you get these giant defects. You get 95% density. With respect to, if you have a very dense powder on the bed and your melt pool is therefore cooler because you have more powder falling into the melt pool, as well as you have smaller particles as well as larger particles, you might be absorbing more energy from those particles because the smaller particles are a little antenna. They have plasmonic resonance with the laser beam. If you tune everything properly, cutting to the chase, you get a lot more melting per scan track, and you can go to very low energy densities. But typically, you're on the order of about 60 to 80 joules per cubic millimeter printing today. Okay, and with special powders, maybe 20 to 30, 20 to 35. So non-eutectic alloys, I'll briefly mention aluminum 6061. I talked about this earlier in brief. You can see here hot cracking. This is not even etched material. And this is because you have, if you look at the phase diagram of 6061, you have a copper-rich or alloying element-rich phase that's solidifying before the aluminum phase and rapidly solidifying. And the result is, since it has I forget if it has a lower or higher density, but a different density than the aluminum. And in consequence, it solidifies, and then the aluminum solidifies because they're different densities in the solid form. Then you get these cracks in your rate structure. And then this material is more or less useless for any structural applications because it's full of cracks. If you're very careful, you can get no cracking. This is by using a different AL6061, which where the melt pool doesn't heat up as much. In this case, a denser one, but also changing the scan parameters aggressively to get more rapid solidification, so that you have less time to phase separate. Another thing you can do is you can just heat up the build bed to 300 or 400 degrees Celsius. And there are only certain printers that can do that, but that helps as well. So the things you can do with both the processing parameters and the alloys themselves and the powder to address some of these problems with non-eutectic alloys, for example, in aluminum. There's a company out there that adds zirconium hydride or something similar to their mix, and the zirconium prevents the formation of these hot cracks by creating these very fine grains. You do get something that's that has low elongation to failure. It's more brittle, but you get rid of the hot cracks. So there's some applications for that kind of thing. So changing the alloy chemistry is also a really high potential area. And what you need to do is change it in such a way that you avoid these types of issues, as well as changing the scan parameters and changing the powder. There are lots of variables you can play with. And the result is you can eliminate pretty serious metallurgical problems if you're careful. 6061 is not available commercially for laser powder bed fusion, by the way. Uniformity puts out a binder jetting version actually that centers to 99.8% density, full density, if you will, 99.7%, and that has material properties that are comparable to ingot. And it's an interesting material, and it's interesting why that happens. We'll get into the physics of sintering in a little bit. We just won't go in as deep. Okay, so I won't walk through all these parameters. This is just a short list. But if you're going to simulate this properly, and if you're going to address the physical characteristics, these are just some of the metadata you need to look at in order to have a reproducible experiment. So if you were going to take data that's out there and do some work on it, use it in simulations, try to do large data analysis, try to learn from it with machine learning or other mechanisms, you would need to be tracking most, if not all, of these items in order to be sure that your results were accurate. And I think I've given a couple of examples, right? The build bed temperature, I think I even forgot to put this on here, but makes a massive difference in aluminum 6061 hot cracking, right? So your mechanical properties would be radically different for a build bed temperature of 300 degrees versus 100 degrees, right? So you need to pay attention to that. The powder size, if your powder was 60 micron D50 in monomodal, as opposed to 40 micron D50 in monomodal, you'd see a radical difference. You know, the D90 and the D10 of the powder matter as well. You know, just again and again and again. If you're, this is the biggest problem in I think, in addressing using good, learning from the data that's out there is you need more data. You need to really know what happened, or the conclusions you draw may be erroneous. And then doing all this, the question is, if you are tracking all this, if you do have a stable parameter set, and a stable, when parameter set I mean powder, layering, and scan strategies, beam spot size, the whole story, environment, then there's certain part geometries that you can create that warp and do not warp, that oxidize and do not oxidize, again, very material specific. Aspect ratios you can print and cannot print related to residual stress. This becomes, again, a pretty complicated problem. There's softwares out there that bring this into the thermoelastic regime. I'll get to those in the binder jetting portion. And they can predict shrinkage and warpage. Those are very interesting if they can work. Softwares kind of work, they kind of don't today. They're problems that still need to be solved. So just one more example. This is something that we printed on, I think, last Thursday, and I thought it looked neat. So this is 316L. This part is printed intentionally to demonstrate this, but it's insufficiently supported thermally. And since 316L I think we're at about 1500 ppm oxygen in this build, will in fact oxidize. We're getting above 500 or 600 degrees Celsius because the heat it doesn't have enough, there are not enough pathways for the heat to leave, so you end up heating the substrate high. You'll have different amounts of residual stress if you're that temperature. Great. If you put a support in the bottom of this, instead of having a 0 degree angle, you put a support attaching to the bottom, this goes away. Sorry, I don't have a picture of that. Just one more example of something to pay attention. I think I've covered all my thoughts on existing issues, and I'll leave these for reference if you're interested. But this first point I want to emphasize, all the salient variables are rarely tracked. The ones I put on the previous page, they're never all tracked and published in papers. They need to be, if the data is going to be good. And you know, they're not always all salient, but the vast majority are. They're never all reported. Even if they were, their impact on different geometries, concerning the strong interaction between variables, are not fully known. They're certainly not known when you start changing alloy compositions and capabilities. Scalable strategies do exist, but it's tough to make them reproducible in different geometries of parts because of problems like this. All right. And then there's softwares out there that are really useful and that are pretty advanced. I'll mention that too. Get that with limited success. I'll touch on this final point too. Real-time laser monitoring of layer defects solves most of the problems in powder bed fusion. The commercial problems you see today are, oops, this layer didn't layer well for a few layers, maybe because you had a geometry that began to warp and the recoder blade smashed into that geometry, and then you get poor layering, you get a streak in the build bed. There's real-time monitoring of layers. You use high-resolution cameras and automated image analysis. It's fast, it's cheap. It's available on printers today. It's not widely deployed, but it works. And what it does is it tracks and says, oh, there was an issue with layer 262 through 267. You're going to have a defect there. That's the data's out there for that. That's useful. And on certain printers, it's there all the time. Monitoring of the laser. You have fluctuations in the power delivered to your printers. Your laser might suddenly drop from 100% to 90% power. Again, the newest printers are monitoring the laser in real time every layer, so you can track that. You can learn, oops, we're at 90% power for 100 layers. We may have defects unless we designed a scan strategy that was robust enough to function at 90% power as well as 100%. This solves most of the problems that are existing commercially, but it's not widely deployed yet, and it doesn't solve all the problems. And once again, if you're going to put this part on an aircraft or in the human body, particularly in an aircraft, you really need to solve all the problems. All right, great. I'm paying attention to time and questions, so I'll go a little bit faster through binder jetting. I'll try to build on the powder bed fusion knowledge when I talk about it. All right, so sintering. And we just had an extremely interesting presentation on particle size and necking, which I think went into way more detail than I'm going to go into. But here's what to start with powder. By the way, some of the powder particles have been removed in the imaging of this. My apologies, it's usually dense. 800 C for 2 hours is where you start. 1200 C for 2 hours, here's where you go. There's still pores. You can still see the outlines of the larger particles. These particles, you can see the size scale here. And then, 1250 C for 3 hours. Okay, now we're starting to get into grain growth and final pore formation. Here you're getting to your 99.5% density. I think, again, this is 17.4. First picture happens to be 316L, the next two are 17. There are many, many factors at play in sintering. To say this quickly, a priori models of sintering are just really beyond accurate models, or beyond the capability of the physics right now. There's so much physics involved, the geometries of the particles, their surface roughness, their surface chemistry, just the sintering itself, and I'll point to the top right here. This is a dilatometer measuring a coupon sintering. As you can see, the 17.4 pH, as temperature reaches a certain range, you start to shrink rapidly. You saw that on the previous slide. This is a phase change going on. Then you stop for a bit, you shrink less rapidly, and then you reach a delta ferrite phase. So you have another that becomes stable, delta ferrite phase 17.4, and then you shrink rapidly again. And then you've shrunk about all you can go, and you stop shrinking as rapidly, and you reach a equilibrium where the pores are gone. It's complicated. This is pretty highly nonlinear. It's a little bit easier for some other materials. This is M2 high-speed steel, not quite as crazy in the physics, but I would say there's a lot still to learn and to develop about a priori sintering models. It's complicated. There's a lot to be done. All right, so presuming though, jumping forward and saying, let's say we have a controlled platform. We have a well-known powder, binder, printer, print setting, curing, sintering, furnace, sintering cycle combination, meaning somebody has to have developed all these parameters in windows that are robust and repeatable. That picture in the side right is not a repeatable situation. That's an uncontrolled situation, not a controlled one. The pictures I showed initially of sintered materials, that's a more controlled one. And the binder powder interactions are really important. I talked about powder. Naturally denser powder can do a lot of good. Finer particles have higher mobility, so they can sinter more at lower temperatures, but then they don't spread very well. The rheology is poor. The cohesion is too high. Lower cohesion powder with finer particles is a great idea. I think I'm very subjective. That's one of the things Uniformity Labs does, but it works. So binder powder interactions are important. So when you're layering the powder, are you laying down binder in a way such that it's evenly absorbed? And the printer itself has many different print heads, tens of thousands. They jet picoliter size drops or nanoliter size drops at a very rapid pace. Are they jetting them properly, repeatedly? Are the nozzles getting clogged? It's a hard problem. But you can get repeatable systems is what I'm getting to. Even in a repeatable system, this is something that went wrong. The powder surface chemistry was wrong. We did this on purpose to explain what it was. And therefore, you got bad layering of dry powder on top of bound powder. And you didn't get as much dry powder down on top of the bound powder. And you can see that how the recoder was moving right to left. You can see how it's sort of pushing these wave patterns. And then when you centered this part, that's not a part you'd be happy with typically. All right, great. So once you have a controllable system, you have the problem of geometries again. Is it controllable for all geometries? Or when you center, you're going to fracture. So you might see a fracture point at sharp edges in centering if your part is large enough, even in a controlled system. And it depends on the alloy, it depends on your peak centering density, it depends on your parameter, highly dependent. So you will get warpage. The warpage is hard to predict. So binder jetting is great. It's cheap. You can get control, relatively speaking, you can get controlled systems. And I have this other, list again of all the parameters I've been talking about. I think these are important, but again, I'm not going to walk through and talk about everyone. These are never all reported, but particularly in binder jetting, maybe they need to be. They need to be tracked to get good correlation between your actual output results and your parameters, your input parameters, even in a controlled system. Okay, but even in a controlled system, and I borrowed this from Desktop Metal's website, this is their life center, the thermoelastic model that pre-distorts a part. So here's the CAD on the top left. When you center it, you get this warp due to the centering dynamics in a thermoelastic sense. So forget about particles. Let's pretend the particle problems are taken care of. You have a controlled repeatable system. Even then, you do have this warp that's introduced by the shrinkage. You can address it through these thermoelastic models, which there are many. Live Center is one of them. Live Center will iterate and pre-distort the part. So you'll print this. Then when you put it in the centering oven, it still distorts, but it comes out as this. So far less distorted part. The ability to do this is important for binder jetting because if you can do it, it can be applicable to larger and larger parts, making this a viable technology in the hundreds of thousands of tons, not just in the maybe low thousands. I don't know what the other comparison is. So there are technologies out there can do this. To do this properly, you need a controlled system. You need to know it's controlled. And then from that controlled system, you can use thermoelastic modules instead of powder centering physics, which are very complicated. Thermoelastic physics are still complicated, but less complicated. And you can build these programs that lead to this result. The same concluding thoughts. All salient variables rarely tracked. They should be. If you're going to use algorithms to address this, you need to have all the variables, or at least the vast majority, or you're going to have uncontrolled results that are not reliable. And data is even less often collected in jetting, although there are ways to collect it in controlled experiments, and some folk do, but you need to get that data. And then I'll jump to the centering. Once you have a controlled system, one thing you might be able to do is use data analysis, big data analysis, machine learning too. And this is just one suggestion, by the way, but to predict warping or to see what the uncontrolled warpage is. So pre-distorting is great, but you still want to know at the end of the day, there are variations in the powder bed. The powder bed might be 52.3% dense on the right side and 52.5% on the left side. So you need to predict what type of warpage or uncontrolled warpage or shrinkage you're going to have as a result of that variation. And you need that because you need it in a commercial setting if you're going to manufacture at scale. You need to assume the worst case at 99.9% repeatability and then solve for that case. So just predicting what those variables will do, those changes will do, it hasn't been done very well, would be very valuable in getting some kind of predictive simulations. It's a lot of work, but interesting nonetheless. And that would help the industry. All right, great. So you need repeatability before you can deploy. Right now, jetting is only repeatable with very small, kind of compact parts. There are folks out there trying to make it repeatable for larger parts. For example, Uniformity by using its powders. Desktop Metals, GE has a binder jetter coming out. HP. There's lots of good work being going on there. There's lots of things they're doing that is beyond their capability, like the ideas I was talking about a minute ago. There's too much physics involved. There's too much math to deploy commercially. Data processing is enormous. And I think there's a lot of opportunity there. All right, great. Thanks very much. I'll pause there, and hopefully there's a few more minutes left for questions.
Thank you, Adam. This is very, very interesting talk. Thank you. Do we have any questions from the audience? Yeah, sure. Go ahead, Mark.
Hi, thanks, Adam. A really nice talk. This is outside my area of expertise, but I'm curious. You did mention about surface chemistry and the environment during the process of sintering, the impact. I mean, I'm coming from the chemistry side, so I know nothing about what's being done in this area, but it would seem like it's pretty ripe for process chemistry, surface chemistry, whether it's almost independent of the process used to make the part, whether it's the bed or the binder or the laser, that, you know, surface chemistry, whether it's in the process or liquid phase, it could play a huge role in this. Has much work, my question is, has much work been done and using these techniques to assess the benefits of using interfacial chemistry to help in some of these manufacturing techniques?
Yes, and I can say there has been a lot of work done in the commercial space, but we don't, and I'll be quite honest, we don't fully understand what we're doing. It's more of the engineer shotgun approach. We tried this and it worked, and we know what's happening, but we don't know why it's working. I'll give an example. For binder absorption, it's very clear. You need to I'll take 17.4 pH, for example. You need to bake that powder at above 180, 200 degrees C. You need to get some oxygen into the surface, a little more than is produced by the gas atomization processes. Or you typically won't absorb, for example, an aqueous binder. So you won't be enough wettability to get even absorption. So there's a binder powder interaction. Then going to the sintering, you also see an advantage in sintering after baking the powder. We think because there's more oxygen, it's interacting with the carbon in the binder. That's a well-known interaction, carbon plus oxygen and steel equals better sintering. You do remove both the carbon and the oxygen, you form carbon monoxide during the process, but it could definitely be far better understood. And you see rather radical differences, even with the same sintering cycle, if you've, for example, baked the powder versus you haven't baked the powder, for certain powders, right? It really depends on how the powder was manufactured initially. Powder roughness matters. Water atomized powder may not need to be baked where gas atomized does. Even a bigger deal, say one other comment about it, perhaps even a bigger deal if you're sintering aluminum, something that and again, here's a plug here, but it's a reasonable one. We're the only ones who are able to sinter 6061 to full density, as in a 99.5, 99.8% dense uniformity labs. And that's because of these different sizes of particles that are entrained in the material. You start with a denser brown part, you end up with a, qualitatively speaking, a denser sintered part. You have liquid phase sintering. But I'll tell you what, if you don't worry about that oxide layer and the processed gas during the sintering,
right,
you're gonna have trouble, because you got to get rid of that oxide, and its melting temperature is not aluminum's melting temperature, it's double that.
Yep.
But if you have finer particles, you have more dangling bonds, you have more surface mobility of the oxide. Maybe you can get rid of it more easily. But yeah, so the gas chemistry during sintering is absolutely critical. And there's some known from the MEMS industry about steels, but there's so much more that could be done here.
Thank you.
Thank you, Adam. Any other questions from the audience? Okay, so if you know, I do have a question. I think this is a very interesting talk and a lot of information. I'm trying to absorb at least some of them. So one key question that I think I get is that, you know, especially when we talk about the binder jetting technology, which is probably the future for the 3D printing for the low cost and large scale products. So you mentioned all of these challenges and all the parameters that could possibly affect the final product, right? But suppose, you know, how could we like formulate a problem that could be solved using like AI or simulation technology? For example, if you're just in a car industry and you just want to produce this particular shaped large scale parts, right? So and just use this particular alloy powder. Does that remove, you know, a large part of the uncertainty or a large part of the parameters so that you can only focus on, for example, you know, how should I design the nozzle for the binder, right? And how should I deposit the binder at different locations just for this particular case? And that seems to me like a more solvable problem, right? Without worrying too much about other parameters, but I have this very specific application domain. and I just want to know what the optimal processing parameters or the real-time control of the printer. Is this a reasonable understanding of the problem?
Yes, thanks, Dr. Zhao. That's I think you've actually answered the question very precisely. If you work through the 9 steps of binder jetting and try to solve them simultaneously from an a priori basis, you're not going to succeed. It does work, and commercially there are plenty of companies out there testing, again, throwing it together. They're smart people, right? They're scientists by and large, but they find regimes that work, but then there's still outstanding problems. And there are certain problems you can focus on, like the alloy chemistry itself. If it's more, and the surface chemistry, if they're more commensurate to good sintering, then it just solves a lot of the concerns about defect formation, about shrinkage, because if you have a particle that's more likely to neck with another particle, for example, at larger radius, then you've addressed the problem quite aggressively. You have a solvable problem. So alloy chemistry is one. If you're looking at analyzing warpage, that's one of the other ones I introduced. As long as you can collect the right data, you can formulate a problem that hasn't been formulated and address a solution to it. What's the impact of, you can simulate it, right? What's the impact of a change in bed? But yeah, I think the idea there is to pick the most salient problems in one of the 9 steps, or maybe 2 of them, and go after those. And you can potentially gain a tremendous advantage by solving one of those, or by changing chemistry, or by analyzing what's going on in that step. And improving one step has a ripple effect. It's going to improve all the steps tremendously instead of going after the whole problem.
Thank you, Adam, for these insights. Very helpful. Let's thank our speaker again. Thank you very much. And if you have any further questions of thoughts on this one, we definitely have this discussion section, which we can talk more about it.